the choice of a coordinate system, which is also referenced or referred to as reference frame or basis, is usually dictated by the inherent geometry or directionality in a problem. Cartesian is not universally applicable, neither is cylindrical, neither is spherical, and it really depends on the geometry. For irregular geometries, it is not easy to obtain a physically intuitive description or mathematical modeling in standard coordinate descriptions of systems such as Cartesian, polar, etc. So what we do in those instances, or what we needs a way to identify directions or vectors that have or that give certain conveniences or simplifications in the description of tensors. Again, you won't found this exactly in these words in the book. This is my narration of what is the motivation to learn about eigenvectors. All right. And some of this you already know, at least the mathematics part of it you would know. In linear algebra, eigenvalues and eigenvectors have the property to diagonalize any square matrix. I'm sure this is not the first time you are hearing about this. What I mean by that statement is, if you have, suppose, a matrix, we'll call it A for now. A has elements A11, suppose A is some matrix. I'm not even referring to tensors at this point. It's just a matrix which you would encounter in a math class, just a collection of 9 numbers. The matrix A can be represented in a form which looks like a diagonal matrix whose elements are, let's say, lambda 1, lambda 2, lambda 3, and all off diagonal elements are 0. Any matrix can be, not any matrix, any invertible matrix can be reduced to this form, where it can be expressed as a diagonal matrix, and these values lambda 1, lambda 2, lambda 3 are the eigenvalues. That is, these two are equivalent in the sense that if you compute the determinant based on this matrix is equal to lambda 1, lambda 2, lambda 3. So it's the same matrix except we express it in an eigen form or a diagonal form whose elements are the eigenvalues. And these eigenvalues satisfy a special property which is A times any vector x is equal to lambda times the vector x, where x is an arbitrary vector. Each eigenvalue has a corresponding, or not has, yields a corresponding eigenvector. It's like saying, take a pause from writing, I'll give you time. If you reduce this matrix to its eigenform, you can then derive three eigenvectors corresponding to the three eigenvalues. And along these directions, the matrix is expressed just in terms of three numbers instead of 9 numbers. So think of it in a measurement context. If you are trying to measure some kind of a tensor, say for example stress, ideally or usually if you just adopt a Cartesian coordinate system, you would need to measure 9 components of the stress. But if you identify the eigendirections of that quantity or that tensor, you just need to measure three components or three values in those specific directions. And these three directions, the value of, we call it x1, x2, x3 are, I'll give you time, don't worry, okay, are the eigenvectors. And these three directions are mutually orthogonal, which means they are independent directions, and they can be used to define a basis or a coordinate system that is natural for that quantity or tensor or shape. So ultimately, the answer to this, whatever I've written here, need a way to identify. That way is basically to take a tensor, which is represented by a matrix, reduce it to eigenform, get the eigenvalues, use it to obtain eigenvectors, and use the eigenvectors to define the coordinate system. So today, most of the time, we are going to get into the practice of computing eigenvectors for any given matrix or any given tensor, which is a matrix. Okay. So I'll give you time now. Have you written down this part? Can I erase this left side? So I'll write the flow chart like this. To me, identifying the natural coordinate system for a given tensor reduces to an algorithm. That algorithm is, so identifying natural coordinate system for any tensor. To me, that algorithm starts with, so tensor A, we'll call it any tensor A. The components of A may be specified in any coordinate system to begin with. For example, Cartesian to begin with. The second step in that process is to compute the eigenvalues of A. So some of you may know, remember, some of you may not remember. Question is then how do we compute eigenvalues? Eigenvalues are obtained by solving determinant of A minus lambda I equal to 0. Oh, actually, then that means I forgot mentioning one thing. So I said this any matrix can be reduced to a diagonal form, right? This diagonal, these values have a property that lambda is defined by the value that can be written as A can be written as lambda times I. That's what this statement is. If you say these two are equal, it's like saying lambda, that is any value of any of the three values of lambda can be used to express the tensor or matrix A. So by taking the determinant of this equation, we get a cubic equation for a 3 by 3 matrix, which yields lambda 1, lambda 2, lambda 3. You might sometimes get them to be distinct from each other. Sometimes you might get two of them to be the same and third being different. Or sometimes you might get all three equal to each other, and we'll see cases of all of them. Okay. So step one is to first express the components of the tensor in any coordinate system. Step two is to compute the eigenvalues. Step three is to evaluate the eigenvectors x corresponding to, or I call this x alpha, corresponding to lambda alpha, where alpha takes values 1, 2, and 3. And how do we do that? We try to write A times x equal to lambda times x. Again, these two I've just written as equations. I'll show an example where we'll see how to do the actual math. Okay, so this is just the principle. X alpha, where alpha takes values 1, 2, and 3, are or can be used as basis vectors for a natural coordinate system. We're going to see examples on this now. So what what I've described so far is in section 2.5.3 of the book. So if you want to read this from the book later, that's where you will go. All right, so at this point, I can give a problem that is purely symbolic, that is give you a tensor in terms of symbols and make you do the eigenvalue calculation. But to keep it easy, just to illustrate the process, I'm going to give you a matrix in terms of actual numbers, and we'll try to get the eigenvalues for those and go through this exercise so that it's easier to do with numbers than with symbols. Okay. Just give me 1 second. I need to pull up a file. All right. All right. So let's try. Um, I'm going to have a matrix. That's 1, 1, 2, 3, minus 1, 1, minus 1, 3. So this is a matrix. I'm not saying tensor, just a matrix for which I want you to compute the three eigenvalues and the corresponding eigenvectors. That's the question. It could be an exam question in a math course where the vectors of the matrix doesn't mean anything, but for us, this matrix represents a tensor, and that tensor can be related to stress or strain or some other kind of physical quantity. Okay, so where do you begin? What's the first step? The, yeah, that's the goal. Where do you begin to do that? Um, that's okay. I'm going to give you a technique which will work not only for numerical problems but also symbolic problems. So first step, what you want to do is set up the equation determinant of a minus lambda I equal to 0, which is called the characteristic equation. So that's like writing determinant a, that is minus 1, or a, what is a minus lambda I? A minus lambda I is equal to this matrix minus 1, 1, 2, 3, minus 1, 1, minus 1, 3, 4, minus what is lambda? Lambda is some scalar which is not yet known. And what is I? I is identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. So this is A minus lambda I, which you can write as minus 1 minus lambda 1, 2, 3, minus 1 minus lambda 1, minus 1, 3, 4 minus 4 minus lambda. So this is A minus lambda I, and I want you to take the determinant of this matrix and set it equal to 0. So that's like writing determinant of minus 1 minus lambda 1, 2, 3, minus 1 minus lambda 1, minus 1, 3, 4 minus lambda equal to 0. Whatever number can be as components of this matrix, your first step is just to write the same components and subtract lambda from the diagonal elements and equate that determinant to 0. This is the universal starting point. So what would this equation be? This is, if I expand, this is minus 1 minus lambda multiplied by minus 1 minus lambda times 4 minus lambda minus 3. That is this term multiplied by this subdeterminant. And then second term is minus 1 times 3 times 3 times 4 minus lambda minus here is minus 1, here is 1. So minus of minus 1 times 1 plus 2 times 3 times 3 is 9. This is minus 1. This is minus of 1 plus lambda. So minus 1 minus of 1 minus lambda equal to 0. This is nothing but a cubic equation for lambda, which you have to solve to obtain 3 values or 3 roots. Let's do that. I mean, I'm spending 10-15 minutes to go through this process today, but from the next time I'll say, here is a matrix, keep ahead to what are the eigenvalues, and assume that you would know everything in between and you'll be able to do it yourself. So maybe you can simplify and cross check what I'm doing, because I could make some mistakes. So just do it on your notebook and then look up. Okay, you don't have to wait for me. Are you getting this or something else? You need to double check and tell me. Let's do that. It's plus. Okay. So if you check if 1 is a root, 1 plus 2 minus 11 minus 10. It's minus 1 a root. So this is 10. No, this is 13. This is 11. Are you getting this equation? Yes. Okay. Now we need to think of a solution to this. What is the solution? Each equal 10. Okay, I'm going to make a. All right. Do we have anybody who has a calculator and provide the solution? Because I don't want to spend all my time solving this and the class time is wasted. So I'm going to instead do something else. You followed the process so far, it's the same thing, except I'm going to change my question for which I have the answer so that I can illustrate the process. Okay. We are not going to spend all our time solving a cubic equation. So minus 2, 2 minus 3, 2, 1 minus 6, minus 1 minus 2, 0. Minus 1 minus 2, 0. So I'm changing the question to this matrix. The process remains the same. And what we are going to have from here, the characteristic equation determinant of A minus lambda I equal to 0. And the characteristic equation happens to be minus lambda cube minus lambda squared plus 21 lambda plus 45 equal to 0. This is the characteristic equation for this matrix, and the three eigenvalues are 5 minus 3 minus 3. The solution to this is lambda 1 equal to 5, lambda 2 equals lambda 3 equals minus 3. So I've just given you the eigenvalues which you would get by solving a cubic equation. Now the question is how to derive the three eigenvectors. That's the question. Are we up to speed? Like I changed the question. Did you notice that? You're okay? All right. So to do this, first you would start with the one of the eigenvalues, which is the unique one. What is the definition of eigenvector? Definition of eigenvector is that it is a vector when multiplied with the matrix, it equals a scalar times the vector itself. So we are trying to determine x. Assume x has components x equal to x1, x2, x3. We'll just assume it has three components which are non-zero in general, x1, x2, x3. And now we'll try to solve for what are x1, x2, x3 so that we can figure out what that eigenvector is. All right. So here is A. This matrix here, minus 2, 2, 0. Sorry, minus 2, 2, minus 3, 2, 1, minus 6, minus 1, minus 2, 0, multiplied by x1, x2, x3 is equal to what is the lambda one we are considering here? 5 times x1, x2, x3. This is the literal implementation of the definition with lambda taking the value 5, and for the next eigenvector lambda will take the value minus 3 and so on. So I would, yeah, I'm making a matrix. Yes, you can do it that way also. There are a lot of equivalent ways to do it. So I'm just going to give you like one of the ways that I'm familiar and comfortable with, and it's also sort of intuitive. So if I expand the right side, it is minus 2x1 plus 2x2 plus or minus 3x3 equal to 5x1. All I'm doing is expanding or multiplying this row with this column. First row with the column vector. If I do the same for the second row, 2x1 plus x2 minus 6x3 equal to 5x2. Go on, tell me.
2x2
Minus 2x2 equal to 5x3. So you can simplify each line by writing minus 7x1 plus 2x2 minus 3x3 equal to 0. 2x1 minus 3x3, I'm sorry, 3x2 minus 6x3 equal to 0, which you can further simplify as x1, sorry, no, you can't simplify that. Never mind. And then third equation is minus x1 minus 2x2 minus 5x3 equal to 0. We're doing this right? No, this is 1 minus 4, not 2. So this has a common factor 2 throughout. So I'm going to rewrite this x1 minus 2x2 minus 3x3 equal to 0. All right. Correct. Minus 2x1 plus 2x2 minus 3x3 equal to 5x1. 2x1 plus x2 minus 6x3 equal to 5x2. Minus x1 minus 2x2 plus 0x3 equal to 5x3. So when I simplify this, minus 2 minus 5 plus 2 minus 3, 2x1 minus 4x2 minus 6x3, which simplifies further as x1 minus 2x2 minus 3x3 equal to 0. I have minus x1 minus 2x2 minus 5x3 equal to 0. All right. Any suggestions what we want to do next?
taking x1 value and substituting in both equations.
Okay, we can do that. That is, you want to say, let's look at equation 2 and 3. Let's try one thing. Suppose you label this 1, 2, 3. What happens if you take 2 and add it with 3? You get minus 4x2 minus 8x3 equal to 0, or you can write x3 equal to or 8x3 equal to minus 4x2, or x3 equals minus 1/2 x2. Okay, we have already used equation 2 and 3. Yeah, if we take 1 and 2, well, you can add it because, yeah, you can subtract 1 and 2. I'm sorry, add 1 and 2. You're going to get minus 6x1 minus 6x3 equal to 0. So maybe what I'll do is I'll write x2 equal to minus 2x. So here I have x3 or x1 equal to minus x3. I've used all three equations now. I can't do any more equations. But only thing I have is x1 in terms of x3 and x2 in terms of x3. Wait, there is one more combination we could do, right? Can we take 1 and 3 and do something about it? If you take 1 and 3, what do you do? 1 plus 3, what do you do? Minus 8x1 minus 8x3 equal to 0, which is same as this equation. So you're not getting any more information. All you know is x1 is minus x3, x2 is minus 2x3, and x3 can be anything. So if you choose x3 to be some arbitrary value, it just will be that x2 will be minus 2 times that, and x1 will be minus 1 time that. So the vector, if the components are x1, x2, x3, which I'll call as x1, that is x corresponding to lambda 1, that is minus c, minus 2c, and c. Or this is c times minus 1, minus 2, 1, where c is an arbitrary constant. Arbitrary meaning you can pick a value you like. Can be 4, can be 24, can be 31, any value. The way we have written this vector x, what is its magnitude? What is the magnitude of x? Magnitude of x would be c times square root of 1 plus 4 plus 1, which is square root of 6. So if I divide by the magnitude, I'm going to write here, if I take x and divide by its magnitude, I'm going to get 1 over square root of 6 times minus 1 minus 2, 1. This is my first eigenvector corresponding to the eigenvalue of 5. Okay. Now we'll have to repeat this exercise for minus 3, and then we have to do something slightly different for the third eigenvalue, which also happens to be minus 3. Okay. So just making sure the answer is correct. So this is correct. Minus 1. Yeah. So this is correct. I want you to try for the eigenvalue or eigenvector corresponding to the minus 3, and we'll do the third one together. Okay, try now. See, one of the key ideas in this three equations is that they are not linearly independent and they don't have a unique solution, which allows you to express two variables in terms of one, and that one component x3 can assume any value. Means an infinite number of vectors can be possible eigenvectors, but we are interested in the one whose magnitude is 1. We call it normalized eigenvector, so that it can serve as a unit vector for a coordinate system. So this quantity here is normalized and can serve as a basis vector. We still can't fully say that because we have to see whether it is orthogonal to the other vectors that we'll derive, but I'll tell you it will be true. That's why I'm writing it here. Questions? Anything not clear? Yes, ma'am.
The 5 next to our x's at the top came to mind. Over here, the lambda 1.
Yep. Yep, this is lambda 1. You can start the next round of eigenvector calculation by starting here. Just replace 5 with minus 3 and proceed exactly the same, but a different set of values will come. You're going to do that. You do it and then look up. Yeah, I'm also going to do it. I'm going to erase this. Or actually, I'm going to start here because the left hand side is not going to change. The only thing that's going to change is the right hand side where I will write minus 3x1, minus 3x2, minus 3x3. Left hand side will not change. So I'm going to write x1, x2, 3x3 equal to 0, 2x1 plus 4x2 and 6x3 equal to 0, which is same as x1 plus 2x2 minus 3x3 times 2. And then third equation is minus x1 minus 2x2 plus 3x3 equal to 0, which is same as writing is minus 1 equal to 0. So if you look up, what are we getting here? If you look at the three equations, it's just really one equation. The first equation multiplied by 2 gives the second equation. First equation multiplied by minus 1 gives you the third equation. So it's really that you have only one distinct relationship between the three quantities. So you can take, say for example, you can write x3 or x3 equal to, to keep it simple, I'll write x1 equal to 3x3 minus 2x2. x2 and x3 can be chosen arbitrarily. Okay, say for example, if you choosing x2 equal to 1 and x3 equal to 0, what do you get for x1? 0 minus 2 minus 2. So
In equation 3, x plus 3x3.
Wait,
If minus 3x3.
plus 3x3, you are correct, plus 3x3. So if I pull out minus 1, it will become minus, right? So minus 1 times minus 3 will give me plus 3.
So it will be 2x2 plus 2x2. Plus 2x2. It should be plus 2x2 if you take minus.
Oh, yeah. Plus 2x, right. Okay. So anyway, I wrote it incorrectly, but my point remains that they are really the same equation. So when you write it this way, you should make choices for x2 and x3, which are again linearly independent of each other. Meaning, if you made a choice 1, 0, making another choice, like for example, c, 0 doesn't make sense because it's just simply, so if you write for x2, x3, if you write c times 1, 0, for any value of c, it's the same choice. So if you have chosen 1 and 0, then what is the vector? X vector is equal to minus 2, 1, 0. First thing you have to check is make sure this is again not another form of the first vector. So this is okay, this is a valid choice. Okay, suppose, oh wait, you've chosen this, right? What is the magnitude of this vector? Square root of 5. So you have to divide this by square root of 5 to normalize the vector. So this is x corresponding to lambda 2. Now what do you do about the third eigenvector, which is also -3? If you went through the process, you will end up exactly at the same spot. What do you do? Take different but distinct values. So if you did 1, 0, maybe again we'll do x2 equal to 0, x3 equal to 1. So in that case, x corresponding to lambda 3 would be, what is x1 in this case? 3 minus 2, or 3 is just 3. So 3, 0, 1, and I have to divide this by square root of 10. So my three eigenvectors are -1, -2, 1 divided by square root of 6, -1, 0 divided by square root of 5, 3, 0, 1 divided by square root of 10. Question: are these the only possible set of eigenvectors for this matrix? No. Why?
Can take different values.
You could keep taking different combinations which are linearly independent and generate a whole infinite set of eigenvectors. Like for example, just for argument's sake, you can choose x2 equals pi and x3 equals e. Just for argument's sake, this is a unique combination. Suppose this I do once, the second choice I make is x2 equals square root of pi and x3 equals cube root of e. Again, for argument's sake, these two are linearly independent of each other. So I would be getting completely different set of eigenvectors. The only common eigenvector is the one corresponding to the first eigenvalue, which is distinct. So the moral of the story is, you take any matrix which represents a tensor, reduce it to the characteristic equation, obtain the roots of the characteristic equation, which will be either 3 all distinct, 2 distinct and 1 similar, or all 3 are equal, or all 3 are the same. Accordingly, you will be able to derive 3 eigenvectors, which then will be used to represent that tensor. So for example, this tensor here, or this matrix here, can also be equivalently represented as 5 minus 3 minus 3. Okay, this form is called eigenform. All right. Not only that, are we all done writing? Anybody needs some time to catch up? Mr. Wright?
I'm just doing this.
Okay, I'll give you time. Good. All right. So henceforth, I will just say, excuse me. Henceforth, I'll just say here is a tensor or a matrix, and you'll be able to immediately say what the eigenvalues are. That is, you don't need to tell me how, but you just need to show me the values. So I'll say this is 5 minus 3 minus 3. And what are the eigenvectors? Eigenvectors are x1 or x lambda 1 is equal to 1 over square root of 6, 1 minus, so minus 1 minus 2, 1, x lambda 2 is equal to 1 over square root of 5 minus 2, 1, 0, and x corresponding to lambda 3 is 1 over square root of 10 3, 0, 1. The rest of it, all the details, we'll assume that we know, okay? All right. And to be consistent with the book, I'm going to use the symbol gamma 1, gamma 2, and gamma 3 to denote the eigenvectors. With me so far? Can somebody tell me what have we done so far? Get the eigenvector. So now we will use gamma alpha, where alpha runs 1, 2, 3, to define a basis. What is the definition or requirements for a basis? It should be mutually orthogonal and should have unit magnitude, which are combined and said mutually orthonormal. So any three mutually orthonormal vectors can serve as the basis vectors for a coordinate system. So you need to check, you don't have to check every time, but at least now we have to check, are these three vectors mutually orthonormal? How do you check that? You take gamma 1 dot gamma 2, or if you take gamma alpha dot gamma beta, this should be equal to gamma alpha beta. That is, if you take gamma alpha dot gamma alpha, you should get 1. Sorry, let's say gamma 1 dot gamma 1. If you say gamma 1 dot gamma 2, it should be 0. Can you check that just manually? It will be true. I just want you to check it. So let's take the first two vectors. Gamma 1 dot gamma 2 is equal to 1 over square root of 30 times 2 minus 2, 0. 2 minus 2 plus 0. So this is good. What is gamma 1 dot gamma 1? Of course, it will be 0 because we ensured it, right? So that is also okay. And you can check this. Sorry. You can check this for the other directions as well. Gamma 1 dot gamma 3, etc. and so on. So these three vectors will be used to define a basis vectors. So you can write tensor A. If you write that as Aij times Ei that is the Cartesian basis or Cartesian representation. This is the Cartesian representation. You can also write this as summation alpha equals 1 to 3 the lambda alpha, the eigenvalue, multiplied by gamma alpha. I am representing the tensor in terms of the basis vectors as in terms of the eigenvectors as the basis vectors. I don't have to write the combination. So if I expand this, what am I going to get? I'm going to write lambda 1, gamma 1 plus lambda 2, gamma 2 plus lambda 3, gamma 3. I don't have to bother writing the off diagonal terms like gamma 1, gamma 2, gamma 2, gamma 3, and so on and so forth, because in the diagonal matrix, those terms are all anyway zero. Those components are zero. So you can expand this out and you will find that it is exactly equivalent to this. You can check it. You should check it. That is, you can take what is gamma 1? Gamma 1, gamma 1. You have 1 over 6 times minus 1, minus 2, 1 multiplied by minus 1, minus 2, 1. You can do the multiplication, you will get a matrix, you will get another matrix, you will get another matrix. If you add all of them up, you will end up with a lengthy exercise, but you can try this in your free time. You have something like this. Why am I writing it like this? To generate the to generate all the components of this vector. So you know, in matrix multiplication, if this is 1 by 3, sorry, this is 3 by 1, or I should write it down. So this is 1 by 3. No, also not correct. 3 by 1 times 1 by 3. Okay, let me do it the other way. So what is gamma 1? 1 over square root of 6 minus 1, or I'll write minus E1 minus 2 E2 plus E3. Right? And what is gamma 1, gamma 1? That is like writing 1 over 6 minus E1 minus 2 E2 plus E3. Again, I have to write minus E1 minus 2 E2 plus E3. This is the dyad in principal coordinates. This is the dyad in Cartesian. You can expand this out. This will come out as E1 E1 minus 2 E1 E2 minus E1 E3 and all such combinations. And you do this for each of the terms, add all of them up, you will end up with this matrix. So the point here is this tensor A can be expressed in a Cartesian coordinate system which has no physical significance, and equivalently it can also be expressed in terms of its eigenvectors and eigenvalues in terms of in the principal coordinates, which has some physical significance or give us some mathematical simplicity. This representation is called spectral representation of a tensor. That is, you are expressing the tensor in terms of its eigenvectors instead of some arbitrary, unphysical, unrelated coordinate system. Now, why am I harping so much about this principal direction? What is intuitive about this? The only physical example I would give right now is that when you are designing components, if you look at any cross section, you can work out what is the principal stresses using your Mohr search. Physically, you tell me what is the significance of those principal directions or principal stresses. It would give you two directions. One along which the tensile stress is the maximum, the normal stress is the maximum, and one perpendicular to that direction where the stress is purely shear and has the maximum possible value. That is, it gives you two directions in 2D I'm speaking, where the stresses are maximum and either purely compressive or purely normal or purely shear. That represents usually the planes where your failure or any kind of deformation could happen. So we are always interested in the principal directions. It has some physical significance for that problem. That is the concept behind taking any particular tensor and using the tensor itself to define principal directions for that point. Okay, so as a computational exercise, whenever we encounter a tensor, what we will first do is reduce it from some coordinate system into its spectral form. So this is going to repeatedly be asked of you. Whenever you see a tensor, first thing is reduce it to spectral form. Okay, so get comfortable with this. I want to suggest you to try problem 2.14, and in fact, I want to just start the problem today. It's one of the homework problems, I think, 2.14. Okay, so let's try that now. Example 2.14. Take a look if you have the book. So problem 2.14 says a tensor A is given as A equals alpha times I unit tensor minus E1, E2 plus beta times E1, E2 plus E2, E1, where alpha and beta are scalars, E1 and E2 are orthogonal unit vectors. Now note that the symbol for dyad that the book uses is looking like this: E1 cross with into in a circle, cross within a circle, E2. This is what the book uses for dyad. What I use is E1, E2. I just want to clarify that. To me, I don't know why they do this, because if I do this, I'll then be confused, or when we do cross product, I'll definitely mix it. So I just want to use this. Okay, so this tensor A, if you write it in matrix form, how will it look like? A is alpha times unit tensor 1, 1, 1 zeros minus alpha times E1, E2 is non-zero, everything else is zero. So E1, E2 is here 1, or I can write plus alpha times minus 1, and everything else is 0. Plus beta times E1, E2, E2, E1 are non-zero, so 1, 1, and everything else is 0. This is the matrix representation of this. So this will be the not spectral. This is dyadic. This is the matrix. Spectral is what we are going to do next. Did you say? Here, I'm just looking at each term as a separate matrix. I'm looking at I know how I looks like. If I look at E1, E2 multiplied by alpha, that's like saying only this element is -1, everything else is 0. And if I look at beta, you can expand this out, you will end up with exactly minus alpha times E1, E2 plus beta times E1, E2 plus E2, E1. Okay, so this is in terms of E1 and E2, which are, let's say, Cartesian or even not even, it need not be Cartesian, it could be some arbitrary coordinates. Question is, what are the principle? And whenever I hear the word principle, in my mind I go, what is the natural directions for this matrix or this tensor? So you can club all this, that is, you can combine all this and write it as a single matrix, which will be alpha minus alpha plus beta 0 beta alpha 0 0 0 1 or alpha 0 0 alpha. This is the matrix, and now you have to figure out what are its eigenvalues. How do you, in fact, the problem says it gives you what are the eigenvalues and asks you to prove that those are the eigenvalues. So it's almost like giving you the answer and asking you to prove. So how do you write down the characteristic equation? That will be determinant of A minus lambda I equal to 0, which is like writing alpha minus lambda minus alpha plus beta 0, beta alpha minus lambda 0, 0 0 alpha minus lambda equal to 0. It's really straightforward. Alpha minus lambda times alpha minus lambda squared minus beta times minus alpha plus beta equal to 0. So one of the eigenvalues is alpha. Straightforward. This is the quadratic equation, so it's like writing lambda squared minus 2 alpha lambda plus alpha squared plus beta squared minus alpha beta equal to 0. I'll let you deal with this. Okay, these two eigenvalues will get something like lambda 2 comma 3 equal to minus b, that is 2 alpha plus minus square root of something divided by 2. You're going to get something like this. So I'll let you deal with it. That's difficult. I'll do the easy one. Okay. So lambda 1 is alpha. To obtain gamma 1, which corresponds to lambda 1 equal to alpha, we write A times x equal to lambda 1 times x. What is A? Minus alpha plus beta 0, beta alpha 0, 0 0 alpha times x1 x2 x3 equal to alpha x1 alpha x2 alpha x3. So if I expand this, this is minus alpha x1
Plus alpha.
This is plus. So plus alpha x1 minus minus alpha plus beta times x2 equal to alpha x1. I just multiplied the first row with the column and equate that to the first element on the right side. I'm getting alpha x1 plus minus alpha plus beta times x2 equal to alpha x1. So if these two go away, alpha and beta are given to be scalars, and there is no reason we should assume that they should be equal to each other. If they are not equal to each other, the only way this is true will be when x2 is 0. There's no reason we should assume that alpha is equal to beta. Okay, we assume that x2 is 0. Okay, now let's take the second equation and see what we get. Second equation is beta times x1 plus alpha times x2 plus 0 times x3 equal to alpha times x2. So this is irrelevant. 0 times x3. x2 is anyway 0, so this goes away, this goes away. And you have beta times x1 equal to 0. The only way that is possible is x1 is 0 if you assume beta is non-zero in general. Now look at the third equation. 0 times x1 plus 0 times x2 plus alpha times x3 equal to alpha times x3. So these two are irrelevant. It's like writing alpha minus alpha times x3 equal to 0, or this is nothing but 0 times x3 is 0. For this, x3 can be anything. x3 can be any value. This relationship will be satisfied immaterial of what that value is. So the conclusion here is x3 is arbitrary. So x1 is 0, x2 is 0, x3 is arbitrary or any value, which means gamma 1 is basically 0, 0, 1. Because it's arbitrary, you can write it C and then you have to divide by the magnitude, which will again leave you with 1. So one of the principal directions happens to be the 0, 0, 1 direction, or what we might otherwise call E3 or Z-axis. Okay, so this is gamma 1. I want you to evaluate gamma 2 and gamma 3 by yourself. That's part of the homework. And in fact, the book also gives you what gamma 1 and gamma 2 have to be, which you can cross check. So gamma 1 has to be 0, 0, 1. So we are right so far. And these two you need to compute and verify. So this whole principle, taking any tensor A and representing it as alpha equals 1 to 3 lambda alpha times gamma alpha. I told you this is called the spectral representation, and this is given in equation 2.81 in the textbook. Equation 2.81. Okay, thank you. So I'm going to give you some, like every problem, you don't have to go through all the steps. We are just going to develop some useful results which can skip some or save some time for you later. Okay. So here it goes. So if you have any matrix, which let's say we call it A, and we can write A equals Aij, Ei, Ej, where Ei and Ej could be some coordinate system that you start with. It could be arbitrary. We can write determinant of A minus lambda I equal to 0 yields lambda 1, lambda 2, lambda 3. Of course, you can write this equation as minus lambda cube plus I1A lambda squared minus I1 minus I2A lambda plus I3A. I1, A, I2 and I3 are called the principal invariants. I mean, their name is less important, but what is more important is what is I1? I1 of A or I1A is equal to the trace of A. What is trace of A? A11 plus A22 plus A33. That is in the initial representation. Suppose you had it in a Cartesian form, A11, 12, 13, 21, 22, 23, 31, 32, 33. I1 is the sum of the diagonal elements, which you can write in index notation as I. Since I is repeating, the summation is implied. I2A is equal to the trace of A inverse minus the determinant of A. It looks silly for me to say that I'm giving you this cubic equation and telling you the coefficients of this equation are some complex matrix operations that we need to do. It's silly to say it that way, but think of automating this problem. Think of writing a computer program for which if I give you a matrix or a tensor, it will spit out the eigenvalues and eigenvectors. Suppose that is the goal. In fact, that sounds like a good project problem, doesn't it? Maybe, okay, let's talk about it at the end of the talk. So, if I give you these formulas, you can compute these coefficients systematically. All you need is a subroutine for the trace, the determinant, plug it in the cubic equation, get a solution to the cubic, 3 roots, and for that you need to compute the 3 eigenvalues. Everything can be automated. The goal is not for you to do this manually. You should know it manually, but also use an algorithm to make it do it for you. Okay. So this trace of A inverse minus determinant of A can be written as half GII times GJJ minus GIJ times GJI, or not GA. AIJ times AJI. So it's trace of A inverse multiplied by determinant. And then I3A is simply determinant of A. Okay. So I'm going to stop here. What we have remaining in this first unit is essentially how to differentiate tensors. That is, we have talked about tensor dot product with other vectors. We can talk about vectors, vector operations. We have seen addition, multiplication, contraction, and so on, eigenvalues. The remaining operation is when we talk about quantities like, say suppose you have gradient of a scalar, we know that this results in a vector. If we write the gradient of a vector, that results in a second order tensor, and the gradient of a tensor could result in a higher order tensor. So we are going to see what are these operators, basically differential operators. That's the one of the last major topics in here. All right, in the last minute that I do have, what do you think about writing a computer program that will calculate the eigenvalues and eigenvectors of a matrix? It would give you a lot of practice in doing this manually, and to check your program, you would write it in Fortran, C, MATLAB, or whatever. Don't use any built-in subroutines. Just write the program, all the subroutines yourself, and you'll learn a ton during the process. Are we all up for it? What do you think? We can keep the stakes low. I can say that we have allocated 5% of the 5% for the first homework. I can make this assignment 2% and your other submission 3%. So that it's a low stakes thing for you to do some programming and learn this material. Yes, no? Yes. So along with your first homework submission, develop a program, submit the script, submit a screenshot of the output from your script. You can choose any language that you want. Just don't use any built-in subroutines. Write all these calculations by yourself using for loops. And you can do this for 3x3 matrices. In principle, I should be able to take your little computer script, feed in any matrix which is invertible, and it should give me the 3 eigenvalues and 3 eigenvectors. Good. Okay. So I will write this in the homework problem statement and repost it. So this will also be due by February 25th, when the homework 1 is due. So this segment will be worth 2%. Remaining problems will be worth 3%, and I might delete 1 or 2 problems from the remaining so that, you know, whatever you do here, that work is removed from there. Is anybody opposed? Anybody is like, this is too much work, I don't want to do this? No? You want to try this? Okay. I always appreciate you trying, so I will be eager to give you credit. Okay. All right. See you on Thursday. Thank you.